Hey, everybody. Happy Friday. I'm guessing most of you are going to be watching this on Friday. So happy Friday or happy Monday if you're a procrastinator. But here we go. We're going to be taking a look at radians like we did yesterday or last week, I suppose, but focus a little bit more on the unit circle. So, quick question to get us started here. Charlie, Mac, Dennis, and Sweet D are working in a cornfield, creating large concentric circles. After they finish one third of their largest circle, the local law authority interrupts their work. So the question is, what is the angle if they've done one third of one full rotation? There's a couple ways of looking at this, but I think the easiest way of thinking about this is all the way around a circle is 2 pi radians. That's our definition of what a radian is. So if it's 2 pi radians all the way around and we're looking at one third of that, the answer is simply, if my pen would work for me, 2 pi divided by 3. Now, I know some of you are much more comfortable with degrees. In fact, probably all of you are more comfortable with degrees right now. So when you saw a third of a rotation, you maybe just thought a third of 360, which is 120 degrees. And then you took 120 degrees and you multiplied by that scale factor from yesterday, 120 times pi over 180. And then you simplified that fraction. 60 goes into 120 twice, 60 goes into 180 thrice, and we end up with the same 2 pi over 3, but man, it sure works a lot better if we can think in terms of radians. So, like those of you who have taken a foreign language class, the faster we can go to thinking in that other language, the better off we're going to be. And I'll try to help you out with that a little bit today. If we're looking at the unit circle, these are the significant angles that we're going to have. Just like when we were working with degrees, we saw lots of multiples of 45 degrees and 30 degrees. When we're doing radians on the unit circle, we'll see lots of multiples of those same angles: pi over 6s, pi over 4s, pi over 3s, pi over 2s. Those are a basic foundation, just like 30, 60, 45, 90 were when we were doing radians. Visually, I'd just like to show you this. I've got this unit circle divided up into pi over 3 sectors. And so when we're doing these problems and we're looking at sines and cosines and we're trying to figure out where we are on the unit circle, I'll be thinking when I see something pi over 3, excuse me, I've got 1 pi over 3, 2 pi over 3, 3 pi over 3, 3 pi over 3, of course, simplifies to 1 pi, 4 pi over 3, 5 pi over 3, 6 pi over 3, again, simplifies to 2 pi. And visually, again, you're more comfortable using degrees, so you're thinking about 60-degree rotations, but it's the same picture in our mind as we're counting off pi over 3. And so when I look at 5 pi over 3, I'm thinking, okay, starting in this direction, the positive x-axis, and counting off 1, 2, 3, 4, 5 pi over 3 brings us down there. Looks a lot like a 300-degree angle. Similar if I'm counting off by pi over 6s, or thinking visually about what 30 degrees looks like. 30, 60, 90 is the same as pi over 6, 2 pi over 6, 3 pi over 6. But of course, 2 pi over 6 simplifies to pi over 3. 3 pi over 6 simplifies to pi over 2. And so when I see something like 7 pi over 6, I want to find, hypothetically speaking, tangent of 7 pi over 6. I'll be thinking in terms of pi over 6s. 1, 2, 3, 4, 5, 6, 7 of them puts me down here. 1 pi over 6 past pi, we're down in the third quadrant, making the small reference angle with the x-axis. And then finally, with pi over 4, I'm thinking about visualizing 45 degrees. I've got pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5, 6, 7, 8 pi over 4 brings us all the way around. And I'm visualizing these 45-degree angle sectors as I count them off. So whichever one of these we're doing, just like when we were doing unit circle in degrees, we're going to get either the tall skinny triangle, the short wide triangle, or the isosceles right triangle with a 45, a 60, or a 30-degree angle made with the x-axis as a reference angle, or you could think of it as a pi over 3, a pi over 4, or a pi over 6 angle made with the axis. But that all depends on how far along in translating into radians your brain has come. So All I have left to do with this lesson is to just do some quick examples, give you a little bit of repetition to see what's going on. You'll get obviously more repetition as you work through the assignments. But I'll start with pi over 3. We'll start with a simple one in the first quadrant, sine, cosine, tangent. I'm going to draw this unit circle. Man, I am so sloppy with this stuff. So much easier when I have an actual board in front of me and a marker to hold on to, but hopefully you get the idea. Pi over 3, I'm thinking about pi over 3 is the same as I think about a 60-degree angle on the unit circle. My 60-degree angle gives me the tall, skinny 30, 60, 90-degree triangle in the first quadrant. Everything's positive over here, so this should be pretty quick. Sine is the vertical. The vertical is the long side of the 30, 60, 90, and so square root of 3 over 2. And again, everything's positive up there. Cosine is the horizontal. It's the short side of the 30, 60, 90 triangle. So that is our 1/2. And then finally, tangent is sine over cosine, vertical over horizontal, square root of 3 over 2 divided by 1/2. 2's will end up canceling out, and we'll just end up with positive square root of 3. A quick note, if you didn't see it, I did goof up on the notes from the previous section. The last question that I did, I think I had an angle that was down in the fourth quadrant, and I didn't pay attention to the negative sign value. And so I believe it was even the same answer. It was square root of 3, but it should have been negative square root of 3 because in the fourth quadrant, sine is negative, cosine is positive, so that should have been a negative value. All right, that is that one. Let's increase the level of difficulty a little bit. Let's go to a non-first quadrant angle, and we'll throw in the reciprocal relationships here as well. I'll make a quick sketch of my unit circle, as I'm sure many of you are doing as you're working through this, or maybe you just have a unit circle drawn out that you refer to as you do these problems. Here we go. I'm thinking 3 pi over 4. Now I realize, again, some of you are maybe taking that and multiplying by 180 over pi and simplifying fractions. I'm going to think of this in terms of I know what a pi over 4 looks like. A pi over 4 is 45 degrees. I've got 3 of them. So I'm going to count off 45 degrees starting at my initial side over here. I'm going to count off 1 pi over 4, 2 pi over 4, and here I am at 3 pi over 4 pointing up into the second quadrant. The pi over 4 reference angle, the 45 degree, means I've got an isosceles right triangle over here. This diagram's actually not looking too bad. Both of these are square root of 3 over 2. This one is a positive square root of 3 over 2 because it's up. This one is a negative square root of 3 over 2. Excuse me, I think I just misspoke twice. Positive square root of 2 over 2. And this one's a negative square root of 2 over 2 because it's going to the left. So that gives us sine and cosine. Sine is positive root 2 over 2. And cosine is negative root 2 over 2. While I'm writing this, I'll also let you know that I have changed the setting on the quiz. So at this point, you can go back and take a look at questions that you got wrong. And I'm sure a lot of you are going to notice that a lot of the points that you lost were on the signs. And by signs, I mean SIGN, the positive or negative answer. And it's I don't know, it's picky, but if you have positive and it's supposed to be negative, that is just as incorrect as having the wrong number. So be careful of that. Don't worry, you'll have a test where you'll be able to make up some of those points coming up at the end of this chapter. Okay, moving along. Sine is positive, cosine is negative, so tangent will be negative. And since the value is the same, we'll just have -1. We like tangents of 45-degree multiples. Cotangent is the reciprocal of tangent, so no problem there as well. And then for secant and cosecant, let's see, cosine was negative, which means secant will be negative. Sine was positive, so cosecant will be positive. And then when I think about the reciprocal of the square root of 2 over 2, 2 over the square root of 2. And when I rationalize that denominator by multiplying by the square root of 2 over the square root of 2, we end up with just, well, 2 times the square root of 2 on the top and 2 on the bottom. So the 2 ends up canceling out with that 2. And we end up with, well, negative root 2 for secant and positive root 2 for cosecant. There we go. I guess I could pause and let you think, but this is a video, so if you would like to pause, you could do that anytime you like. Moving along, the last example I would like to do with you today is 7 pi over 6, which, again, go ahead and multiply by 180 over pi if you would like to make the conversion that way. I'm not going to say that's wrong, but I am going to encourage you to start thinking in terms of radians, which for this problem means that I'll be thinking in terms of pi over 6s. Ooh, look at that horizontal line. Check that out. Sorry, distracted by my own penmanship. A pi over 6 looks like a 30-degree angle. And so when I'm looking at 7 pi over 6, I'm going to be counting off 30-degree angles or pi over 6s, and I'm counting 7 of them. So starting at my initial side along the positive x-axis, I'm counting 1, 2, 3 pi over 6s, 4, 5, 6 pi over 6s, and 7 pi over 6 brings me just a little bit past horizontal. Looks like I've got the short, wide 30, 60, 90 triangle. I'll have a negative square root of 3 over 2 for my cosine value. For my sine value, the vertical is the short side, so it is 1/2, and it's going down, so it is a negative 1/2. Since both sine and cosine are negative, that means my tangent will be positive, my secant will be negative, my cosecant will be negative, and my cotangent will be positive. Let's see what these values are. Tangent, sine divided by cosine, so that would be 1 divided by the square root of 3. But if I have 1 divided by the square root of 3 and I rationalize that denominator, that'll end up being the square root of 3 over 3. And I feel like at this point we've done that enough that I won't write it out. I'll just refer to the fact that you'd have to do rationalizing of the denominator to get to that. As long as I'm thinking about tangent, if this came from 1 over the square root of 3, that means its reciprocal is the square root of 3 over 1. So I'll call that the square root of 3. Again, positive because I'm in the third quadrant. And then finally, secant and cosecant. Let's see, secant is the reciprocal of cosine. So flipping cosine upside down, I've got negative 2 divided by root 3. But after I rationalize that denominator, I'll end up with 2 root 3 over 3. And then last but not least, cosecant is the reciprocal of sine. Reciprocal of negative 1/2 would be negative 2 over 1. I'll call that negative 2. And so there is third quadrant. Fourth quadrant works the same way. That's not a new step for us. So there is our unit circle. I'll leave this one up. Some of you may want to use this as a reference as you're working on these types of problems. So you could print off this slide specifically. It's got a lot of information on here. The only thing that bugs me about this one is that for some reason, when they printed this off, this 210-degree angle should be down here, as should, oh, that 360 is okay. Yeah, so I don't know. That one angle they put in a weird spot. But there we go. Continue on working on the homework. I've received a few questions from a few people, but not too many. So in this distance learning environment, if I don't hear from you, I assume that you're doing okay. As long as you're turning in homework assignments and moving along. But if you have questions, certainly get in touch with me. Otherwise, have a great weekend. Or if you're a procrastinator, hope you had a good weekend and you're ready for a new week of school. See you next time, guys. Have a great day.